we present Descriptive Non-photorealistic rendering, a text visualization approach for documents pertaining to physical subject matters. In this approach, we aim to create a visualization that is grounded in the real world, one that can be recognized and the data can be explored based on real-life metaphors. We constructed a vocabulary to describe the subject matter by extracting the part operation from a lexical database called WordNet. The result is a tree that describes the hierarchical organization of subcomponents contained in the physical subject. We then use a vocabulary to do two things. One, we analyze document and calculate a score for each component in our subcomponent vocabulary. And two, we map the subcomponent to a segment 3D model, using the calculated score from the text to guide the rendering process. Here we have a visualization of a vehicle complaint database. Our vocabulary comprises of words that makes up the vehicle, and we chose to look at occurrence statistics. In other words, how many times was a particular component mentioned in the text corpus. A yellow, orange, red coloring scale is used to determine the rendering color. High occurring components are more red and more opaque, while less frequently occurring components are more yellow and transparent. Thus, parts that are frequently complained about are given more emphasis and appear to pop out to the viewers. Components that do not occur at all in the complaint report take on a different style altogether. They are drawn in a faint outline style to provide background context to other objects. Our prototype system is composed of four major components: a 3D visualization that shows an overview, a lens widget for data exploration, a heat map that shows detailed information, and a document widget that displays the actual text. Finally, we have a set of domain-specific filters used to manipulate time and organizational hierarchy of vehicle manufacturers. The 3D visualization is interactive and allows viewers to view the model from different vantage points. An item can be selected directly on the model, which will limit the visualization to documents pertaining to the current selection. Selected items are marked with a blue silhouette. The remaining items will have their score recalculated to reflect the co-occurrence relationship. That is, how many times did these items fail when the selected item also failed. Multiple items can be selected to allow investigations of a general or a very specific problem. The lens is a detail-on-demand widget that varies its content based on its location. This, together with the 3D model, allows viewers to define logical regions which is otherwise difficult to do with abstract representations. For example, one might ask, what are the issues with the front portion of the car? The lens widget pulls out detailed information of components underneath it in the form of heat maps. The lens can be moved to any location on the display, resized to cover more or less area, or cut into the model to show and select hidden objects. The heat map provides detail at the lowest granularity level. It is organized into a grid, with months arranged from left to right and years top to bottom. The heat map facilitates finding trends, patterns, and outliers within the selected time frame. There are three different modes: a component mode, which shows patterns for a specific item, a monthly mode, which shows the most complained about component at a given time, and the global mode, which is a combination of both. It is used to show global outliers. Comparison view allows us to make item-to-item comparison of different types of the same parent object. For example, between two different car models. It is activated when we select a vehicle from the Vehicle To filter. Here, the outline color indicates which vehicle has the higher rate of complaints, and the opacity of the outline indicates the strength of the difference. The fill color reflects the overall importance within all components, where the importance is based on the number of occurrences. The aggregation view arranges items into higher-level logical groups, allowing viewers to see subsystems rather than individual objects. For example, here we show the seat subsystem, revealing that overall it received a high level of complaints. We conducted an evaluation with 12 participants. Each participant completed a series of computer-based tasks while we observed how they interacted with the system and if they were able to use a visualization to facilitate decision-making. Feedback and observation results were positive. Participants were generally able to solve analytical tasks with the aid of the visualization. In addition, subjective feedback indicated that they found it fun and enjoyable using the 3D visualization in conjunction with the lens widget. We have presented descriptive non-photorealistic rendering, a text visualization approach based on real-world semantics. Thank you for watching.